I'm Harley Mackenzie, this is Peter Nunn. We're both from Hard Software, which is a technical software development company that we've been in operation for about 16 years, mainly in the energy industry, though we've done some work in the health industry, insurance, finance and risk management areas as well. Again, we're mainly specialising in producing systems that enable people to trade in the competitive electricity market, and I shall give you a very brief introduction of what we do. So basically we're trying to come up with using optimization techniques, analytical work, and basically developing trading systems for people who have to operate in the electricity market. You may not be aware there is a gas and electricity open market that people who generate electricity and produce gas participate in. They have to participate in these markets. We also have to be able to bid or offer our energy into these markets. There's clearing prices and it operates on a dispatch basis. So just to understand some of the things that we'll be showing you, we need to just quickly cover some of the things that we've done. So we've done a lot of work in the renewable energy space, a lot of work in the analytics for the energy markets. We've developed embedded systems basically in the health industry at the moment and doing data analysis and modelling. So why do we have to have a competitive electricity market? Basically, before it all started in December 1998, each of the states independently operated their electricity markets, even though there were interconnections between Sydney and Melbourne through the Snowy Mountains scheme. That was a separate area in the middle of the two regions there. Since then, Melbourne, Sydney and Adelaide started a competitive market where each of the generators bid into the market and then a dispatch. And I'll talk about that dispatch load balancing issue in a second. After that initial start, we subsequently added Queensland into that national electricity market. They came in about 3 or 4 years after the start. And again, subsequently to that, the Basslink happened, which was the underwater connection between Tasmania and Victoria, again, creating their own little region in the national electricity market. So why do we need this dispatch process? Basically, electricity, except in a few small instances, can't be stored. So basically, the electricity markets are a constant balancing between what the regions are using and what they're generating. So basically, we can't, apart from two exceptions, we can't store electricity. There is a scheme in the Snowy Mountains at Jindabyne where they can pump water back up the hill, and that's one way of storing energy and therefore releasing it when they need it later on. And also there are things like battery storage coming into play in the electricity market. That could be a potential game changer in the whole thing. So what happens is that we've got normal generators, we call them dispatch generators, such as coal, gas, water, hydro, and they can basically be turned on and off as required. So you'll have things that run all the time, like the big brown coal-fired power stations, and then you'll have what are known as peaking generators. So they're the gas generators that come on, and hydro, which will only come on when the market requires that information the market requires that generation into the market. Conversely, there is an opposite problem, that when the load drops overnight and at other times of the day, you have too much generation in the market. And because there is limited storage in the market, you have to tell everyone to turn down. So we're going to be talking about intermittent generators, which are wind turbines, and lately solar, which is just coming into play now. So basically, they generate as much as they can most of the time. So basically, the wind blows, they generate as much electricity as they can, and what happens is, especially in South Australia these days, if the wind's really blowing at 3 o'clock in the morning when the load is the lowest, you have too much generation on the system. So newer wind generators now have to be turned off or turned down so that we don't have an oversupply of electricity in the market. So that's the general background. We're involved in basically taking information from a various number of sources. AEMO is the government operator of the electricity market, and they provide all sorts of market data on 5-minute basis, half-an-hour basis, and those things. And there's a huge amount of information that comes through, and that basically gets downloaded into relational database systems. At the other side, our systems are there in between that market and the wind farm generator. So we have to also take a lot of information from their control system. So they measure things such as weather data, met data from their masts, how much generation they're doing from each of the turbines, how many turbines are available for use, and all that information. We also take in user input for things such as when turbines are going out of service and those sorts of things. And also the primary, one of the primary drivers of this dashboard is that we have a whole lot of owners of wind farms these days who are in foreign countries who don't have competitive electricity markets, and they invest in wind farms here, and then suddenly they find they have to understand a whole lot of things they didn't know about. There are competitive electricity markets elsewhere in the world. New Zealand is a very good example of that. Some parts of the United States, in Europe, there are a number of schemes, but most people who have invested in wind farms don't have a lot of experience with this idea that you can actually be turned down. You can't just generate as much as you like all the time. So our requirements here are a lot of data. We're getting 1-minute data, and this is a live feed from a certain wind farm. Oh, no, it's not. No, we're not onto the live feed yet. This is a screenshot. And I'll just briefly close my part of the presentation. The background is that we're dealing with lots of data. We're dealing with data by 1 minute for that main display there. It gets updated on about a 1-minute basis all the time.
1 second live data. Yeah.
Yes, we're incorporating that. We'll go to that at the later part. And we're using things such as live D3 graphs, spark lines up the top, and I'll pass you over to Peter to go through some of those details.
Right, thank you. So basically, as Harley said, this is probably different to most of the Meteor apps that we've seen here, at least anyway, in that it's not so much involved with users putting in lots of input all at once into the thing. This is a lot of data that a smaller number of users are looking at, and they're not really so much interacting with it. The big advantage we found with the Meteor system, the DDP system, is that we can, once that initial data is loaded, the collections update very easily. So basically, as a new data point comes into the Mongo database, an old one drops off and a new one arrives. There's one DDP transaction per data point. It's just brilliant the way it works. The downside to the way we're using it at the moment is that we're duplicating a fair bit of data because we're keeping data in a SQL database as well as in the Mongo database, and at some point we will probably rationalise that because storage is becoming an issue. But the sort of things that you can see that the operators are interested on, on this screen are, on the spark lines you can see that the RRP one, that there was a sudden spike in price. Those spark lines are about an hour's data. So whatever screen the user's on, they can see at a glance what their power's doing, what the wind's doing, and most importantly to the operators, what the price is doing. These bars on the side give them an indication of how many of their turbines are generating at any given moment. It's all colour-coded, so if they start losing turbines, it goes yellow and goes to red, as does the wind speeds. Until I started capturing these screen captures 5 days ago, the dispatch cap was going off fairly regularly. For the last 5 days, the flaming wind hasn't blown at all. In fact, for 3 of the last 5 days, this thing's flatlined. There's been almost nothing on it. We have actually, when I get to the live one, it's actually blowing a little bit down there at the moment. The other thing you can see on this particular wind farm, which is unusual, is that they've actually got a north-south split. So the wind farm is actually split into 2 halves. And D3's allowed us to stack that data up on top of it, on top of the graph, so you can see which half's doing what. So the D3 package has actually done an amazing job for us. On some of the other tabs, we have things like the met data. Now, each of these... market data, not the met data. Harley was talking about the dispatch system. It's actually a linear program that runs every 5 minutes in the background. And it determines who can generate how much and when. And what you have on this graph is the blue line is what the actual, this is price and generation on the other side. The blue line is what was actually generated. The red line is what that model is forecasting it's going to do for the rest of the day, basically. And consequently, how much money they've made and what the generator's forecast to make in the day. And that is surprisingly accurate. I haven't shown the Met tab. Oh,
Okay.
I will go to that in live one. On this graph is a schematic of their switch yard. And again, it's done with, what did you use this?
SVG.
SVG, that's right. So these elements are all live. So if the circuit breaker's open, that circuit breaker symbol will open, that line will go black. And so it gives them immediate feedback of what's happening. Again, these are guys who haven't got access to the SCADA system. The SCADA engineers will know all of this because they've got access to really fine detail. But this is aimed at the managers, I suppose, the higher level guys who, A, you wouldn't trust with the SCADA system, and B, wouldn't know how to drive it if they had one. So,
and traders.
Oh, that's right, yes. And the guys who are actually selling the power also use this as well, as it turns out. There are a few other things on here that I haven't got screenshots of, which we'll show you a few of. There's an alarming system behind this, so we can set alerts on various parameters. If they change, it will send SMSs or emails to whoever you've configured to do it. And the bit we haven't quite finished yet is that there's a requirement for the operators to put in what their projected availability is of the turbines, so they can put their maintenance schedules in, they can put in unplanned outages, and that all gets reflected back to AEMO to put into that model. And that we haven't quite got that going yet. We're trying to work out a nice way to do timelines for them to handle that.
They can plan unplanned outages.
Yeah, all right. Thanks so
There's
much.
unplanned outages and then there are planned outages.
Yes. Okay. We'll come back to that. To show you what it looks like live, I hope. Why can't I get that to change? All right, we'll go this way. So here is a live dashboard. Oh, it's done some funny stuff there. Spark lines are a bit out. This is actually running on a, well, this isn't. This is running locally. The system is actually running live on against an Nginx server sitting in a data centre in Sydney. But if we showed you that URL, we'd have to shoot you. So we're running this thing locally across a VPN to get the data in. But as you can see, the wind hasn't exactly blown very hard today. In fact, it's dropped off a bit. Anyway, so they are currently generating 7.3 megawatts. Gee, that's startling, isn't it? Out of 150. And as well, actually, I suppose it shows one thing. You can see that the Met indicator's gone to yellow because the wind's dropped. If it gets to the point where they're actually using power, that'll go red.
The market, Met data, we have to say.
Yeah. We'll go to the market first. Yeah. So that's, again, what the market, well, there's not much of the day left, but that's what it's predicting. Oh, we just updated. The market one you saw update then. So again, as the data comes in and those predictions are updated, the graphs will change as that data comes through.
One part that we haven't talked about is that AEMO actually have a wind and solar resource forecasting system. So that's where they actually can project what the potential wind resource will be for each of the wind farms. And they've also enhanced that recently for the solar because we're just about to launch this for the Moore East Solar Farm. And basically that, for each of the wind farms, determines what they think will be the forecast wind. And actually, there was a lot of scepticism when that was introduced that it would do anything like that. But actually has proven to be quite good as an indicator of projected wind resources for the wind farms.
I suppose, as you can see, from a relatively low wind day, they've still made about 24 grand, so yeah, it's not a bad day run, I suppose. This is the indication of the Met data. Now, each of these wind farms has a number of Met masts on them. They've been there generally for years before the wind farms are set up, and that's how they effectively locate them. Again, this is useful to the traders predominantly because most of the operators are using data off the actual turbines, but it's a display of the data we get. The accuracy is highly questionable. North is certainly not north on this data, but anyway, we display what we get. And again, that's the SCADA page. So you can see whatever page these are on, you've still got those spark lines at the top, which gives them immediate feedback of what's happening. And these can actually be set up to cycle through as well if you put them up on a big dashboard. The only other bit we haven't shown you, I guess, is the alerts, which is just simply a list of what alerts have been sent out over the last however many days we've configured. Was it 10 days or something, I think. So as you can see, there were lots of caps going on and off before I started trying to capture the regions, but anyway, there hasn't been one since. That's really about it, isn't it, I think?
Yeah.
Is there anything else you want to show? So what we...
I suppose there are a couple of aspects we haven't talked about in terms of the application architecture. If we go back to the main page. Again, we've designed the dashboard sort of to basically use module. Basically, we've designed the dashboard to be interchangeable components. So each of the wind farms will have different SCADA points available to us. So we actually have written an interface into each of the SCADA systems through a number of their protocols, such as I guess you probably may not have heard of this, but DNP3 is a common one, Modbus, OPC. These are sort of control level ALG protocols. So basically we have an interface into their control system so that we take the data from AEMO with the semi-dispatch caps, send it to their control system, verify that it's been received, and also using that interface we extract out important information from the SCADA that we can use in the dashboard and they can use for trading applications. Because even though we're in the day where technology is at a stage that this shouldn't happen, quite often they have a SCADA workstation sitting in an office at the head office, and they literally have to take a USB key and transfer it to something else to be able to get stuff out of it, because that'll be highly secure and attached to their SCADA system, so they have to make sure that there's no unauthorised access and all these restrictions. Whereas the traders would like to actually analyse what was the wind speed versus how much electricity they were generating and all those things which they need the SCADA information from. We also, behind the scenes, have implemented a whole REST API for all of these systems, so that any of the information that we're capturing from the MET system and everything is available through a REST API, so that people can actually use this as a one-stop shop. They can use it for the visual representation of the data, and they can also get the information if they want to write systems that need this information to extract it from. One other thing we haven't shown is there's a slight shading that's going on behind the graph. One of the concepts in the electricity industry is this idea of peak and off-peak power. Often contracts are written for peak, which is from 7 o'clock in the morning till 11 at night, and off-peak's everything else, and weekends are all off-peak. So contracts are always very commonly structured on those bases. So it's important to know when you're looking at the market data or you're looking at the wind data, when your wind is being generated, because you'll be getting very different amounts of revenue from whether it's happening in a peak or an off-peak period. I think that's about it. If we did have a dispatch cap, apart from seeing it on that orange line would go down to a value on the graph, the dispatch flag down the bottom would go red, and whatever the total cleared, which is the amount of electricity you're allowed to generate, would go red. Also, you'll notice there's a section there called conformance. So if they send you a dispatch cap and your wind farm keeps generating above 6 megawatts above what you're told you can, that will change to off target and then not responding, then non-conformance, and then you'll get people ringing you up and it gets very nasty from there on.
So we send lots of alerts by it.
Yes. So apart from that, it's a bit of a different application than possibly you've seen Meteor being used for, and we'll welcome any questions or anything.